Okay. Yeah, I guess it's time. It's time to start. So what you have seen. So first of all, an organizational matter. Next week there will be no lectures. There's going to be the workshop, next door, and the 10th of October is Thanksgiving here in Canada, so there will be no lecture because of this. So the next lecture will be in 2 weeks. Okay, exactly 2 weeks from now. Okay. Now we have seen during our what was Monday the definitions of measure of Gromov-Hausdorff convergence on one side and of gamma convergence of the other. Okay. Now here is the the basic theorem that links them, which is the following. And the first goal for today is to understand the statement of this theorem, and then we will prove it. And the statement is that basically, let me say normalized spaces, for finite and even infinite. So measure Gromov-Hausdorff convergence is equivalent to Moscow convergence of the relative entropies. Okay, but I want to to explain what this means. So if you remember, one of the things that I said, so let's I leave it there, but I will comment later on. So one of the things I've mentioned last time was that the effective domain of the energies typically can change along gamma convergence. So you remember that. So if I define the domain of a functional as the set of points where where the functional is finite, I mean not plus infinity, okay, then typically if I have En that gamma converges or Moscow converges to some infinity, well then what we have is that the domain of the limit functional is included in the Kuratowski limit of the domains of it. All right, you remember this? Am I speaking nonsense? Right? And typically this can be disjoint from all of these. Okay. So the typical example is, the silly example is En is just finite, say 0 at xn plus infinity everywhere else, and then xn is converging to x infinity, and the limit. So the limit function will be the infinity will be the function making 0 just in x infinity and plus infinity everywhere else, and that is a perfect example where the domain of finiteness are disjoint, but it doesn't they are converging. Okay. In this. Similarly, if we have Mn which is weakly converging to a measure M infinity on a given common space, then the support of M infinity is included in the Kuratowski limit of the supports of M. It's a little bit of a first little analogy, very little vague analogy between gamma convergence and weak convergence, but we can sort of build on top of this a notion of convergence of functionals defined on a sequence of varying spaces. So say that we have xn metric measure spaces measured Gromov-Hausdorff converging to x infinity. Okay. Then by definition, this means that there is Y complete separable and isometric embeddings, iota n, isometries, isometric embeddings, such that iota n push forward Mn weakly converges to iota infinity push forward M infinity. By definition, right? Now, so let's call this the collection of the space Y and the embeddings a realization of the convergence. So once you have a sequence which is converging in the measure Gromov-Hausdorff sense, and you fix a realization, once you fix a realization, you can give a meaning to xn points in the capital space xn converging to some point x infinity in the limit point. by definition, this means that, once you see these points inside the given big space, this converges. Right? Of course, the definition depends on the chosen, realization, but let's fix it. Okay? But the dependence is not that big in some sense. Okay, I'll comment in a second what we learned. Now, if you have, say, now a sequence of functionals, let's say En, defined from Xn to R bar, whatever. Now, once we have this notion of convergence of points, I can say what it means that, say, I can define the gamma lim, let's say, of the Ens. This would be, and the gamma lim sup, these would be functionals from X infinity to R bar. And how are they defined? Well, the gamma lim of En at the point X will be the inf, of the limit of En Xn among all the sequences. The inf is taken among all the sequences Xn that converge to X, and with Xn belonging, Make sense? Once you remember, basically to define gamma convergence, I only need the notion of convergence of points. So once I know what it means, convergence of points. This is the same as saying, thinking this En, so same as. So you define En, if you want, tilde from Y to R bar by putting, En tilde of Y is equal to En of X if, Y is equal to iota N of X, and plus infinity otherwise. So basically, you are thinking those functions defined on the space Y plus infinity where they were not previously defined and as the original function. Okay, and then this is true. So then the gamma lim gamma lim sup of these functionals, when one after will be, so what am I saying? So the the gamma lim inf of the En hat is equal to the gamma lim of the En. I guess to say this composition, this composed I infinity is equal to this on X infinity. And the same with the gamma lim sup. So I'm saying that the limit functional, basically, if you evaluate at points on the image of X infinity, that's, okay. And I do this with functionals on points, but I can do the same with functionals, say, on probability measures. So I can say, for very the same way, I can say that mu n probability measure on Xn is weakly converging to mu infinity, the probability measure on X infinity, if iota n push forward mu n is weakly converging to iota infinity push forward mu infinity. In weak convergence as probability measures now on what? Well, I'm putting all these spaces all together in this big space. There's nothing more like that. Okay. And similarly, I can say that mu n is W2 converging to mu infinity if W2 of these measures. Iota n push forward mu n comma iota infinity for mu infinity is going to 0. Right? And I can, and once I have these notions of convergence, I can speak about gamma convergence of functionals on the space of probability measures. And, gamma convergence should have an underlying topology. So I could speak gamma convergence with respect to weak convergence, or with respect to W2 convergence, or with respect to both, in which case I'm speaking about Moscow convergence. Okay, this is stronger than this. So in some sense, this is my strong convergence, this is my weak convergence when I think about measures. Make sense? Now a word about the dependence on the realization, because of course all this depends on the chosen realization. If you come with a different realization, you might say, okay, my gamma, so my sequences will converge to different points, therefore my measures will converge to different points, so I will gamma converge to different functions. Well, yes and no. I mean, yes, but basically this occurs only when there is some auto-isometry of the limit structure. So up to isomorphism of metric measure structures and perhaps functional preserving isometries, this does not really change. So we can agree that let's fix one realization and do computations over there, and things won't change that much if we choose it. Okay. Okay, so now the statement is clear. Right? It means I fix the realization, and after I fix the realization, okay, this function is gamma convergent or Moscow convergent. Questions? Proof. Okay, and MSA. So in here you will see one thing. So as it often occurs, okay, the meta statement. So as it often occurs when either Gromov-Hausdorff or measure Gromov-Hausdorff convergence is involved or gamma convergence is involved, proofs are easy. Okay, so that's one of the power of this concept is that they're extremely general, extremely good, but proving that things gamma converge or must converge typically is easy. I mean, not always. I mean, there are difficult theorems, but typically it's easy. So this implication is basically a joke. Okay, I've noticed this in preparing these lectures. I don't think this ever appeared before. I leave to you as an exercise. Okay, it's a joke in the meaning that it's true, but it's totally useless. Okay, I don't think any use will ever come out of this remark. I thought presented these ways, and even though it was sort of cool from the mathematical perspective, from an aesthetic point of view, but it's totally irrelevant. So the important thing is, okay, that's the crucial. And this is basically what lost Sturm and Villani, well, not Villani / Sturm, proved in their paper. So this implication is the key to the proof of the stability of the curvature dimensional condition. So everything in the end will boil down to this sort of statement. Okay, we will see some statement concerning Sobolev function that is independent on this, but for constants lower Ricci bound, this is your statement. Now, actually, in their papers, they never really mention gamma convergence, not even in the book, optimal transport called the new by Villani is mentioned. But if you once you know gamma convergence and you read their papers, it's clear that, especially from the paper of Lotte and Villani, it is clear that this is what they proved. On the paper of Sturm, this is a bit more sort of a hidden thing, but it's there. Okay. Now let's prove this. So I have to prove two things, right? I have to prove gamma limit and gamma limit. Let's prove the gamma limit. So first of all, so gamma limit. Gamma limit amounts at proving that if you think for a moment that if I have two sequences, let's say mu n mn inside, let me identify now these measures, on xn with the measures on y, and such that mu n weakly converges to mu and mn weakly converges to m, then all these probability measures as well, then the entropy of mu with respect to m is less or equal than the limit of the entropy of mn, of mu n with respect to m. So what is sometimes called the joint lower semi-continuity of the entropy. Typically when one first learns about the relative entropy knows that it is lower semi-continuous, for fixed measure, and as a function on the other, but in fact it's lower semi-continuous as a function of both. Okay. So if I prove this, I'm done with gamma limit. So let's prove this. And this, in fact, is a consequence of the following beautiful duality formula. And by the way, this joint lower semi-continuity has nothing to do with the particular shape of the Boltzmann entropy, meaning integral of rho log rho. Whenever you integrate a convex function of the density, basically you always end up with this sort of. So this kind of statement generalized to those Riemannian entropy that also occur in the study of curvature dimension condition. Okay, and the formula, actually, duality formula is this. So there's a beautiful duality formula that reads like this. So let's define u of z as z log z. And so this is a convex function. It admits Legendre dual. So u star of w. This is the sup over z of z dot w minus u of z. Okay. I mean, you can compute this. This is like e to the w minus 1, but doesn't really matter. So take a convex function over here, you take this other, the convex dual. And now the interesting thing is that the entropy admits the following dual formulation. This is the same as this is the sup over phi in, say, CB of the integral of phi dm minus the integral of u star composed phi d mu. I think it should be this way. Yes. Okay. And this sup is also, I could also take this among or on phi Borel and bounded. I'll mention this for later. Borel. So let me comment on this. First of all, if I prove this duality formula for phi continuous, this lower semi-continuity statement is done, right? Because for fixed phi, so this, so here there is a coupling between the measures here, I'm just the sum or difference of two functionals, right? And each of these, for given phi continuous and bounded, this is weakly continuous in M. U star composed phi is a continuous function, so this is weakly continuous in mu. So the difference of two continuous functions is continuous. I take the sup, it's jointly lower semi-continuous, right? So if I prove this and that, okay. And how do I prove this? Well, not hard. Okay, the full proof requires some approximation procedure, but I can quickly convince you that this beautiful formula is in place. And this has to do with the duality of the properties of the Legendre transform. So given that the function u is convex and lower semi-continuous, okay, I should extend, I should say that u is plus infinity if z is negative. So that this sup makes sense among all the real z. So not only u star obeys that formula by definition, but also u of z is actually, the dual of u star. I think I gave you an exercise about this some time ago for functions on Rn. Okay? This is on R. Okay? The dual of the dual, if you start from a convex function, the dual of the dual is the function itself. Well, but now let's have a look. Okay, I will skip some technicalities, but the basic idea is this. So the entropy, so let's say that mu is equal to rho m. I should discuss also the case where this is, the measure is not absolutely continuous, but let me skip that. So then the entropy of mu with respect to m, this is the integral of u of rho dm. Okay, actually, let me put it this way: is u, let me exaggerate with the notation, u of rho of x dm of x. Right? Now pick your preferred function phi from y to r. Let's say bounded Borel, just to be sure that things remain integrable. Okay. and use phi of x as w in here. This is greater or equal than the integral of rho of x phi of x minus u star of phi of x dm of x. With equality, if I pick, okay, when is there equality? There's equality if, use it, should mention this, is actually equal to z dot w minus u star w if, what it is, w is equal to, I don't remember. Anyway, so the soup is realized, what I want to say. With equality, if 4 were chosen, fine. 4 were chosen. Phi of x. Okay. I should remember when this is. So I think that when I guess that when e to the w minus 1 is equal to z. I mean, we can compute, we make a derivative. So this means two things. So first of all, let's have a look at what is this expression now. Now everything, let me say we row bounded. Let me just row bounded just for, let me exaggerate with the assumptions. If rho is bounded, actually I don't need it. Rho was in L1, phi was bounded, so this is in L1. Okay. So phi was bounded, u star of phi remains bounded by this because I know what it is. So this is really the difference of the integrals. Now the integral of phi rho dm, this is the same as the integral of phi d mu. So okay, and then I remain minus the integral of u star composition phi dm. Okay, that's, I mean, more or less the end of the proof, right? So I proved that. So I proved that this inequality, but I also know that for some well-chosen phi that in principle is just a, is a Borel function, I can get equality. Okay. Okay, and then there's an approximation argument to say that, sort of some dominated convergence and stuff like that, to be sure that I can actually, I'm not claiming that this is the max, I'm just claiming this is the soup. So you can approximate maybe the optimal measurable phi with a well-chosen sequence of continuous functions. Make sense? That's basically all the idea, right? Okay. So joint lower semi-continuity. What about the gamma-line soup? So I need to prove for any nu in, let me say, P2 x infinity that I'm thinking as a subset of P2y, there exists a sequence mu n in, let me say, P2y, such that mu n is now W2 converging to mu, because I'm speaking Moscow convergence, right? So in some sense, the gamma-lim soup should be in the stronger topology, with the lim soup of the entropy of mu n with respect to the measures mn less or equal to the entropy of m infinity, mu with respect to m infinity. That's what I need to prove, right? Now, as a first remark, and this is valid whenever one wants to prove a gamma-lim soup argument, I don't really need to do this for every mu infinity. It is sufficient to do so, to prove so, for mu infinity ranging in a set dense in energy. This is a concept that in calculus operations appears quite often. What does it mean, density energy? It means that not only, let's say D, density energy, this means that for every mu in P2, say x infinity, there exists a sequence, okay, nu, now let me call differently, nu n inside this set D, such that on one hand I have, the density, so this is that, and the, in this case, the entropy of nu n is converging to the entropy of mu. Here we have one fixed functional, which is the entropy with respect to the limit measure, right? And I'm thinking density energy means, of course, with respect to that functional, means that I have a set which is at the same time dense, but where I can, while approximating my stuff with measures on in this denser set, I can also approximate the energy. So, for instance, deltas or singular measures are weakly dense, are also dense, W2 dense, but they are not dense in energy because the entropy of any singular measure is always plus infinity. So I cannot, approximate it in entropy, right? All the measures. Okay. Of course, in general, whenever you have convergence, you have a lower semi-continuity statement, right? So that's, in some sense, it's asking that there is no loss, no drop of energy. Does it make sense what I'm saying? Now, it's quite clear by a diagonalization argument that if you can prove the existence of these approximating sequences just for mu infinity belonging to some set density energy, then you're done. Okay, what's the general argument? Well, I pick a generic mu infinity. I first of all approximate this in energy. Then for every n, I pick nu n. Now for this nu n, I can build the approximating sequence, realizing the gamma lim sup, and then I act by diagonalization. Okay. Now, what it is this set density energy that I pick? Pick D to be the set of measures mu equal rho m for rho, which is rho m infinity, continuous and bounded. Infinity makes no sense, of course, on one. It's not hard to check that measures with density which is continuous and bounded are density energy. The density with respect to the W2 distance is quite trivial, I would say. And whenever I approach, so okay, perhaps let me point out this to you. So let me try to convince you that this set is density energy. So if I pick mu, which is singular, then density in energy, I just need to, this condition is trivially satisfied. So I just need to, because by the semi-continuity, I always have a lim inf. But given that this is plus infinity, the lim sup is automatically satisfied. So this is trivial. I don't understand what is this sound. It looks like I thought it was the projector, but okay. Anyway. So for mu, which is singular, I just need to approximate my mu with in W2 with respect to measures in that class. But the fact that measures with continuous bounded density are weakly dense, that's not hard to check. Okay, weak and then W2 exercise. Okay, that's not that much of a difference. What about approximating also the entropy in the case a measure is not a singular? Well, if mu, let's say, one can do like this. Say that mu is equal to rho m for some rho that now is in L1. Okay. One thing that we can start trying is, okay, first of all, we truncate the density rho, and then put a normalization constant. And then it is clear that the entropy of these truncated measures, it is clear that A, these truncated measures are converging Wasserstein, and B, that the entropies are converging, just a computation. Okay, because if you truncate, basically you are decreasing the entropy. Okay, then you are multiplying by the normalization constant, but the normalization constant is going to 1, so that will not destroy. Okay, so now we are reduced to check the case when rho is L infinity. Okay, but rho L infinity is almost like the sum. So this is almost like the sum, finite sum of, say, alpha I. I can approximate in L infinity with alpha I characteristic function of EI for some, it's almost a simple function. I can approximate in L infinity. But if you approximate in L infinity, then it's obvious by dominated convergence that the entropies are converging. Okay. Okay. Now this EI are Borel. By interior regularization, I can say that this, by further approximation, this EI I can take them compact and disjoint. Okay. And once you have a finite number of compact disjoint sets and their characteristic functions, you can interpolate between them in a continuous way. And without increasing too much the entropy, because the densities are uniformly bounded. So that's the scheme of the proof, okay, of the approximation argument. So if you accept this, well, now we are done, because now I need to prove this fact, not for an arbitrary limit measure mu, but for a measure mu which has a continuous density with respect to it. And the difficulty in this gamma-lim soup is to exhibit the approximating sequence. So I should pick not a random approximating sequence, because for a random approximating sequence, typically I will have the lim infinite quality. Here I really don't want to lose anything in passing through them. Okay, so I have a limit measure, and I want to find approximating measures whose entropy is actually converged to that of the limit. Okay? But if my limit measure has continuous density, this gives me, a way of, finding approximating measures that sort of look like it. Because if rho is bounded and continuous in Y, of course, I can assume up to, I can assume that rho is not negative. For sure, it was not negative, in the support of M infinity. If it was negative somewhere else, just, take the positive part, and this will continue to be true. So I can assume this. Well, now what can I pick as mu n? Well, look. I want to pick the measure with the same density, but with respect to the difference. And you can tell me, wait a second, I'm not sure. I mean, I'm sure that this is a non-negative measure, but maybe it is not a probability measure. And you would be right. So I should put here a constant Cn, which is a normalization constant, where Cn is the integral of rho d mn minus 1. Okay. Now notice that since rho is bounded and continuous, and Mn is weakly convergent to M infinity, this constant goes to 1 in M. In particular, for all n sufficiently big is not 0. Okay, so this measure is well defined. Okay. And how much is the entropy? Okay. So the fact that this constant is going to 1 should make it clear that mu n is W2 converging to mu infinity. Okay. Okay, I should make one. Okay, wait a second. So I should be a little bit more precise. It is clear, given that Mn is converging weakly to M infinity, that mu n weakly converges to mu infinity. I should work a little bit harder to prove W2 convergence. I will comment on this in a second. Let me just check the entropy first. What is the entropy of mu n with respect to Mn? Well, I know what's the density, right? That's the integral of Cn rho log Cn rho dmn, right? And how much is this? Well, this is equal to, log of the product is sum of the logs. So this is equal to Cn log of Cn integral of rho dmn plus, I guess, Cn integral of rho log rho dmn. Right? Now let's have a look. So what happens here? So rho is bounded continuous. So rho log rho is also bounded continuous. It's not negative. So rho log rho is bounded continuous. So this goes to the to the integral of rho log rho dm infinity, which is precisely the entropy of our original measure mu. So that's the good news. Right? So we are approximating the entropy. Make sense? This goes to 1. What about this term? Well, actually, Cn rho n, Cn, so this integral is 1, and this goes to 0. So the entropy do the correct thing. Okay. So I am done if I actually am able to check that mu n converges W2 to the limit measure of infinity. Make sense? This would be obvious if I had made a smartest choice at the beginning and not limit myself in taking as a D the set of measures with bounded continuous density, but with bounded continuous density with bounded support. If I'm living on measures with bounded supports, then with uniform bounded support, then W2 convergence is the same as with convergence, right? How can I enforce also this condition on D when approximating the density energy? Well, I've already said at some point I was approximating a generic density with finite sum of linear combination of characteristic functions of compact sets, a finite number of those. Now, a finite number of compact sets, the union is still bounded. So now when I'm interpolating between them, there's no reason of getting a measure a function with unbounded support. I can just lay on some big ball. Make sense? So that's end of the idea. Of course, there are a few technical details here and there for what concerns the actual approximation argument, but the idea is there. Questions on this? Okay. Corollary. This is our first, actually definition and then corollary. So definition. So let's say here M. I admit the possibility that M is not finite. Okay, is CD k infinity. Of course, this definition is lost from Villani. If for any mu0, mu1 in the domain of the entropy, actually, let me say, for any, let me be more precise, for any mu0, mu1, let me say equal, rho0, rho1, m with bounded support. And the integral of rho I log rho I dm is finite. And yeah, there is mu t a W2 geodesic from mu0 to mu1, such that the entropy of mu t is less or equal than 1 minus t entropy of mu0 plus t times the entropy of mu1 minus what is k over 2 t1 minus t w2 squared mu0 mu1. Okay. Few comments on this definition. First of all, I did not want to write in the domain of the entropy because I did not define actually the entropy function as a function on the full space of probability measures if the m is not finite. So I took sort of the safe approach and I say, look, I just consider measures with bounded support such that the density log of the density is integrable. And for this, I'm asking the existence of some. Okay. So in particular, if I pick, say, some singular measures, I'm not asking anything about the existence of geodesics. Okay. This has to do with the stability, because if I impose that condition, then I will not be able to conclude the stability, as you will see in a second. Okay, there are compactness issues. So considering the statement, you know what W2 is, perhaps you don't know what a geodesic is. I mean, I've never told you. So let me tell you that a geodesic in a metric space, okay, X is a curve, gamma, I mean, for me, unless otherwise stated, the curves are always defined on 0, 1, okay? Such that the distance between gamma S and gamma T is always equal to the distance between gamma 0 and gamma 1 multiplied by the spinning. So this is the same. So I mean, in a moment we'll speak about speed of curves and length of curves, and this is the same as asking that this curve has length exactly equal to the distance between the endpoints, and it has constant speed. Okay, but if you don't know what length is and what speed is, still this makes sense, and it's okay. Notice that it would be sufficient to ask this inequality for the triangle inequality, because I mean, if you have 0, 1, T, S, and you have the distance between these two guys, the distance between these two guys, the distance between these two guys, by the triangle inequality, the sum of these three quantities must be at least the distance between 0 and 1. So if you have an inequality of this kind every time, you basically are enforcing equality. Okay. Okay. So the theorem that I will just prove in the case of normalized spaces, but of course does not require that, is that this condition is stable under measure Gromov-Hausdorff convergence. And the underlying principle is that convexity is a notion that is stable under gamma convergence. Okay. Theorem. Again, lot Sturm with an E. Let X n, well, let me see, converging measure Gromov-Hausdorff to X infinity, normalized. And Xn is CD K infinity, and here, of course, it's important that the K is the same for n, for every n in n. Then X infinity is CDK infinity. Okay. Proof. Well, let's pick. I need to check whether the conclusion. No. So pick. Mu infinity 0, mu infinity 1. Okay. Embed all these spaces in a common Y, a realization of the convergence. Okay. And think all these spaces just as inside this big space Y, and pick this as in the definition. Bounded support, etc., etc. Okay. Perhaps I'm thinking whether I should make one before a comment. Okay, perhaps let me first make a remark. Let me notice that if let me make this. If m of x is finite, then the W2, so if m is finite, let's say m is 1, then I know what the relative entropy is for any probability measure. I've defined it, and And I can wonder now whether this W2 geodesics exists for any couple of measures in the domain of the entropy. Okay. Then make sense what I'm saying? So not just with those with bounded support. Okay. Then and let me say so, and x CD infinity, infinity. Okay. Then for any mu0, mu1 in the domain of the entropy, there exists mu t as in definition. So I don't have to force myself to work with bounded measures with bounded support. Okay. And why is that the case? Because pick two measures in the domain of the entropy, and let's approximate them. You know, this as before, the space of measures with bounded support is dense in energy, right? So we can find, for given two measures, we can find, find mu0n W2 converging to mu0 and mu1n W2 converging to mu1 with also the entropies converging. Mu0, and the same for mu1. This we can do. I mean, we basically have done this before. Okay. Now, for each of these, for fixed n, I can apply the definition, and therefore there is a sequence of geodesics mu tn W2 geodesic from mu0n to mu1n. Make sense? Satisfying the assumptions. So if I'm able, if I'm able to pass to the limit in this, I'm done. Right? So if I prove that these geodesics converge, perhaps up to passing to a subsequence, to a limit geodesic between mu0 and mu1, by the weak lower semi-continuity of the entropy, I'm done, right? Because is it clear what I'm saying? No? I have this inequality I have with the n's, basically, Tn, mu0n, mu1n, w0n, w1. Now, when I let n go to infinity, by construction of this approximation, this right-hand side converges to the correct thing, and the left-hand side is lower semi-continuous. So I'm done. So all is left to prove is that this admit, up to that this form a compact set, basically. Okay. Now, for instance, if the space, if X were compact itself, this would require a no-brainer because the space of probability measures would be compact. So also weakly compact with respect to W2. Now I have uniformly continuous family of curves with values in the same compact set. Ascoli Argela tell me that the subsequence will converge. Okay. So I really basically really only to find some compactness statement concerning this, and the compactness statement is here. And compactness comes from this bound, because the point is that the observation is that the sup in n and t of the entropy of these measures mu t n is finite. Okay. Perhaps here I need to discard a few n's, a few initial n's, but let me say, I mean, I can assume there's no harm in assuming that not only these entropies converge, but they are uniformly bound. If the first elements of the sequence were bad, just change them. Okay. And then, but then you see that this follows by this convexity inequality, because this quantity is uniformly bounded in n. So if you interpolate with t, they remain uniformly bounded in n and in t. I have W2 convergence, so certainly this quantity is also uniformly bounded in n and t, and therefore that is true. Right? Well, but then what do I do? Well, then basically now the observation is that, and this is a nice observation, the fix probability measure, the set of and fix a C. So for every M, let me say in Py and C positive, the set of measures mu such that the entropy with respect to M mu is less than C is tight. And therefore, relatively compact, weakly relatively compact. I leave you this as an exercise. What's the idea? The idea is that when is it that the entropy, becomes plus infinity? Becomes plus infinity when the density of mu is too big. I mean, when the density blows up. Now, so M is a fixed measure. So M as a measure is tight, right? So for every epsilon, there is a delta. There is a compact, so that outside the compact I have little mass. Okay. Now, so outside a certain compact set, M has little mass. Now take a reference measure mu with some bound on the entropy. How much mass that measure mu can ever give to this small complement of the compact set? Not too much, otherwise it has too high density and makes sense. Okay. So basically you combine this. So with this you get the relative compactness for the weak topology of these guys, right? And so now you're basically done because you extract a subsequence where these guys converge to a limit measure for all t rational, let's say. But now W2 is lower semi-continuous with respect to weak convergence. So basically you are building, and this is sufficient to build you an interpolating measure. Okay. Make sense? Okay. Now, if we know this, then we are done, and then we take a little break. I pick mu0. So I need to prove now I have a converging. Well, perhaps I'm late. So let's do 5 minutes break now, and I prove this statement after the break. Okay. Let's make a small. I don't want to rush this. 5 minutes, not more. Thank you. The curvature dimension condition is stable under measured Gromov convergence. And I will prove this, just for normalized spaces, but as you can imagine, this normalization has nothing to do just because, I only introduce convergence for this class of spaces, but this statement can be generalized in natural ways to, without assuming the reference measure to be finite. And of course, there are analog statements for whatever k and whatever n you put here. Okay, and the idea of the proof is the same, and is to basically use the gamma convergence of the underlying entropy function. So let's prove this statement. So what is the result? I know that for this space is Xn, I always have this, Varstein geodesic connecting measures along which the entropy is convex, and I want to prove that the same is true for the limit. So what do? I pick 2 measures in the limit space, okay? And in fact, given that I have this remark, I can pick them directly in the domain of the limit entropy. Okay. And let me say with finite second moment. Okay, of course this is important because for any domain of entropy, meaning okay, should have said with finite second moments, because otherwise I cannot approximate in Wasserstein. Okay, so I pick two measures with finite second moment in the domain of the entropy, and I wonder whether there is this geodesic connecting them along which the entropy is convex. Okay, and what do? Well, basically I do the same thing that I've done here in the case of a fixed space. First of all I find, and I can find by the previous result, I can find the sequences mu and 0, say mu and 1. These are converging in W2 to mu infinity 0 and mu infinity 1, and with the entropies that satisfy the gamma lim sup inequality. The lim sup of the entropy of mu n 0 mn is less or equal than the entropy of mu infinity 0 with respect to m infinity, and the same for the other. Okay, makes sense? Now, in particular, given that this is finite, and the same for the entropy of mu1, for n sufficiently big, this will have finite entropy. Okay, finite entropy in P2 of xn, therefore, by the definition of, okay, I'm erasing this, I will need this in a second, but anyway. So by the definition of CDK infinity plus this remark, I know that there exists, mu nt, which is a W2 geodesic. I mean, n is fixed, is a W2 geodesic in T from mu n0 to mu n1, such that, let me write it. Well, I don't want to write, I'm too lazy. So let me write it. So Mn, I can use colors. Mn, mu nt, Mn, mu n0, mu n1, entropy with respect to the measure Mn, and that's it. Okay? This is true for every n and every t. Okay, for every n sufficiently big and every t. Okay? Now, as before, when I let n go to infinity, this quantity, satisfies the correct inequality. So the lim sup of this quantity is less or equal than the limit entropy. This also satisfies the correct inequality. This converges because I have W2 convergence of the entropies of the measures, W2 convergence of the measures. So the only thing that is left to do is to prove that perhaps up to possibly past the subsequence, these curves of measures, they do converge to a limit curve, which is a geodesic between the limit measures. If I do this, if I prove that there is some weak convergence, then by the gamma limit inequality, I'm done, because I would have semi-continuity on this left-hand side. Okay, this is really a prototypical of gamma convergence. The right-hand side converges because I've chosen the smart, the recovery sequence, and the left-hand side, I mean, I pass to maybe the sequence is not optimal, but I pass to the. Okay. Well, first of all, again, as before, I mean, the argument is really the same that we have just done before, but on a sequence of Lie spaces. If, by any chance, this space Y on which I am embedding anything is compact, I'm done. So, in some sense, for the compact case, that's all we need to do. All right. For the non-compact case, I need to prove that this set mu nt for n in n and t in 0, 1 is tight. Okay. Let me prove that this is the case. Actually, not really prove, but I use for this, as before, use the fact that the sup in n and t of the entropy with respect to mn of mu and t is finite. Previously, it was the entropy with respect to a fixed measure, and I argued that was sufficient to get the tightness of this. Now the measure is varying. How can I still get tightness? Well, this measure is varying, but these measures are weakly converging to a limit measure. Right? So this is still a tight family. So the argument that I sort of sketched before still applies. You give me epsilon, I can still find a compact set such that all these measures give mass less than epsilon to the complement of the compact. So if the previous sort of line of thought, convinced you, then this should also. Okay. And how do I conclude out of this? Well, I conclude because now if this is tight, well, there are various ways of doing that. Let me argue this way. So for every t rational, I mean that I guess is the first idea that one can get. There exists, a sequence nk such that mu nkt weakly converges to some mu t. Okay, and with the diagonalization, I can find a sequence such that this is true for every t rational, just because these are accountable choices. Okay. Now, what it is so I would like this to be sort of the restriction to rational numbers of a geodesic between, my original measure mu0 and measure mu1. So let's compute how much is it, the distance between mu t and mu s. Well, this is, given that W2 is lower semi-continuous with respect to weak convergence, this is less or equal than the limit of W2 mu nt mu ns. Nk, I should say. But these are points along a geodesic between the measures. So I know by the definition of geodesic how much this quantity is. This is s minus t times the distance between mu n0 and mu n1 and nk. Okay. But now when k goes to plus infinity, this converges to the distance between mu0 and mu1. Okay. All right. End of the proof. See, I mean, now, sorry, end of the proof. Now this is really a restriction, to rationals of geodesics. In particular, the map that takes t rational and returns mu t is Lipschitz. So I can extend by this inequality. So I can extend it to a Lipschitz map defined of U01, and that must be a geodesic, right? And now it's clear that the lower semi-continuity is there on the edge. Right. So end of the. There's nothing conceptual. You really just interpreters need to put in line the definitions. I want to make some comments before passing to the next stage of the series of lectures. So which ones? Okay, so the first comment about this convexity inequality. This is not asking. So if you look, let's say, let's draw a graph of what it is, the entropy of what could be the entropy of mu t along a geodesic as given by the definition. Let's say that we have this is the entropy of mu0, this is the entropy of mu1, right? And what is that inequality is telling? Well, the inequality is telling that basically you should be, the entropy of mu t should be below this line. But that's all it's saying. So it could be something like this. So in principle, I'm not telling that the map that takes t and returns entropy of mu t is convex. This is completely acceptable. Then, of course, you could say, wait a second, but here is, okay, of course, I'm drawing the picture for k equals 0 for simplicity. It says k equals 0, now this entropy is rising, then it's not convex. I mean, does not respect the inequality if I instead pick this guy and this guy. And of course, the answer is that, okay, maybe there is another W2 geodesic connecting these measures and this measure, along which the entropy is bounded from above by the correct. Okay. And then one can counter argue, okay, but why do you give that definition rather than asking for actual convexity? And that's because if I ask for actual convexity, I don't know whether it is stable or not. Okay. Or perhaps proving stability would be harder. Because you really need here what it is that we use to prove stability. We use that on the right hand side, we could pass through the limit, and on the left hand side, we argue by compactness and we get the lower semi-continuity. Right? And in doing this, it was useful that we have a fixed right-hand side, and then we construct our approximation. If instead you ask for convex inequality to hold even for intermediate times, then you are in trouble, because you need to to have convergence of the entropy even at the intermediate times, which is tricky. Okay, and typically false. So things are more complicated. So that's first. Second thing, it is perhaps a good time to mention the following lemma. I want to make some comments about the definition of entropy in general CDK infinity spaces. And I need, first of all, I need the following lemma. This has been basically this has been proved by Sturm in the first of these two ACTA papers. So say that X is CDK infinity, then there exists a constant, and say, okay, pick a point in X. Okay, then there is a constant C, possibly huge but finite, such that the measure of the ball of radius r centered in X is bounded by constant e to constant r squared for every r. So you get a control on how big the measure grows out of the CDK infinity condition. The control is terrible, is e to the r squared. Okay, maybe if you are used to polynomial growth of the volume of the ball, perhaps you should keep in mind that on the hyperbolic space, like really the disk, the measure of the ball grows exponentially, not with r squared, with n r. Okay, but with a factor in front that blows up with the dimension. So it's not too strange to this, and this is optimal because if you take r with the Euclidean distance and the measure, which is like e to the x squared over 2 dx, this is CD1 infinity. So it has this df. Okay. How do you prove this? Well, you prove this by the same idea, and this idea is the same that leads under finite, finite n to the Bishop-Gromov inequality. And the idea is this: you pick. I need to. So first of all, I only need to prove this for r bigger than 1, because for r between 0 and 1, I mean, this is at least 1. If I pick this constant sufficiently big, this is always bigger than the ball of radius 1, right? So I can estimate itself to this. So now let me pick. What did I do? Let me pick as mu0. I just consider the measure restricted to the ball of radius 1/2, centered in my point, normalized. As mu1, I pick the I pick the measure restricted to the ball of radius r, centered in my point. Okay. Now these are two measures with bounded support, clearly finite entropy. Okay. This measure, notice that okay, perhaps I should say I can always assume that x is in the support of the measure. I mean, otherwise things are only easier. So these are positive and finite because I'm always working with measures that are finite on bounded sets. So these are finite number. And now I get the existence. Let me just let me work with general. I get the existence of mu t such that this convex inequality holds. Okay. Now notice the following. So there is so if mu t, so let mu t be a W2 geodesic. And let me draw a picture and then I make a computation. So my starting measure has support in the ball of radius 1/2. Let me draw the ball of radius 1, and then I have a big ball, with this r. Okay. And what this does, this W, this measure, this curve mu t is interpolating between this normalized measure and this other normalized measure. Okay, and what I claim is that, I mean, the measure is being, the mass is being basically transported. So what I want to say is that there is some time for which this mu t remains in the ball of radius one. Okay, so the claim, and I can compute this time. What it is? So the biggest distance that could possibly ever been between a point in here and a point in here is what is 1/2 plus r. That's an upper bound of the distance in the point in the small ball and the point of the big ball. A measure that is, so if I have a curve gamma geodesic, you know, from a point, you know, in B1/2 to a point in BR, after time t, it will have traveled, you know, the distance between gamma t and gamma naught will be at most t times 1/2 plus r. So if t is sufficiently small, so I want this distance to be bounded by 1/2, so that gamma t remains in the ball of radius 1 if it's starting from the smallest one, and this is true if t is smaller than 1/2 divided, you know, 1/2 plus r. Does it make sense what I'm saying? No, so for this t, you know, a geodesic that starts from the small ball and goes in the big ball, it will remain in the ball of mass nu. Okay. Now you should know, to continue, you should know something about W2 geodesics that I did not discuss yet, but perhaps you can believe me if I beg you strongly enough that a geodesic of this form is you know, is made by atoms that are traveling along geodesics on the base space. So what I want to say is that what I want to conclude, I will do this with more detail later on. For the moment, perhaps believe me that because of that, the support of mu t will be included in the ball of radius 1 centered in x bar for t less than 1/2 divided 1/2 plus r. Okay. Does it at least heuristically make sense? You know, I'm moving the mass. Okay, the mass moves along geodesics. That's where I'm asking you to believe me, and therefore by this simple computation. Now, what's the point here? Well, first of all, I want to notice that I do know how much is the entropy of mu0, because I know what's the density, right? So the entropy is the integral of log of the density, in this case, log of that normalizing constant, C0, d mu0, basically. Write the density of mu0 dm, but that's, and so this is a number. So this is log of C0, but of course I know who is C0, right? C0 is 1 over this measure. So this is equal to minus log of the measure of B1/2. And for the same computation, the entropy of mu1 is equal to minus log of the measure of the ball. Okay, so what I conclude, so of course by the CD condition, the entropy of mu t is bounded from above by, okay, I should say 1 minus t that plus t this. Let me just actually, well, 1 minus t log m. I mean, this is a number. I call it alpha, whatever. And then I have plus t time, actually minus t times log of m of br. And then I have minus k over 2 t1 minus t. And what is the distance between these two measures? Well, let me, so each atom of Br must be sent into this ball of radius 1r. So the distance it travels is at most, let's say, 2r. So W2 distance squared is like, you know, at most 4 times r squared. Something that goes with r squared, right? The constant is for sure not the best one that you can put, but let's put it there. Make sense? Okay, now I want to make use of this. And for this, what my argument is that the entropy, so if I call, I don't know, nu the measure restricted to B1 normalized, see whatever, then the entropy, because of this, the entropy of mu t, you know, will be greater or equal than the entropy of nu if t is smaller than 1/2 divided. Basically, what I'm saying is that this is an instance of a more general statement. If I have a measure which is concentrated on a certain set, its entropy is bigger or equal than the entropy of the reference measure normalized to that set. And this is basically Jensen's inequality. Okay, because so let me prove this. Let's say that mu t is rho m restricted to B1. Okay, then the entropy of mu t is the integral of u of rho d m restricted to B1. And this is the same as integrating with respect to you know, the, you know, let me normalize the measure. This is basically new, and then I put one the normalization constant. Why am I doing this? Because now this is a probability measure. U is convex. U is z log z, of course. U is convex. So by Jensen's inequality, this is greater or equal. Then I have this factor in front, and then I have u of the integral of rho d t tilde. Make sense? But I know exactly how much this is because c tilde I can take it out. The integral of rho m is 1. That's the mass. So that's u of c tilde. Right? So I have so this is equal. Let me make the computation. So this is 1 over c tilde, and then u of c tilde. U of c tilde is c tilde log c tilde. Right? So this cancels out, and with by the and that's you know, and that's by the same. So that's the end of the problem. So this guy is greater or equal. Let me write it here. Is greater or equal than the entropy of nu. Nu is the normalized measure on the unit ball. So the same computation as before tells me that this is minus log of m of B1. Okay. And I'm done because now this is fixed. This is fixed. And here I have basically, you know, an r squared. And now you see, this is the guy that I want to control from above. I control so minus the log is on the grid. So bring it out and there. Okay. So this so the basic idea of the trick is to use CD. So what is that I've done? I use the CDK infinity condition to interpolate between measures of two different balls, concentric. I used optimal transport argument to understand how the measure behaves and where the support should be. And then Jensen's inequality, and it gives me the conclusion. Okay. Now, if I could pick, now I had to pick mu0. Why did I pick mu0, the measure on the ball of radius 1/2, than the delta is 0? Because delta 0 is typically infinite entropy, so it's forbidden from this point of view. But in the CDKN case, when Riemannian entropy are involved, taking deltas is in some sense allowed, and this allows you to make you know, a sharper estimate, because when you interpolate between mu r so, sorry, the ball of radius r and delta, you know that, say after time 1/2, you are inside the ball of radius 1/2 without, having to add, little extra terms and so on and so forth. So this is a sharp control on the ratio of the volume of a ball of radius r and the volume of radius r prime with r prime smaller. And if I will not give you any details on this, but basically, if you take the definition of CDKN, apply this sort of trick to contractile balls, what you get is the Bishop-Gromov inequality in the sharp form. Okay, that tells you that the ratio of the volumes is governed by the ratio of the volume in the model space. Okay, of course, I didn't tell you what is CDKN, so you can, but basically it's just a computation. Where just means that the difficult part is finding the CDKN, of course. But once you get that, the conclusion is easy. Okay? Why did I bother you with all this? Because this is interesting for the following purpose, for the following reason. If this occurs, this implies that if I pick, say, let me say, C prime just C plus 1, then the integral of e to the minus C prime distance squared from x bar dm is finite. Okay, up to basically the measure a priori on a CD infinity space can certainly be plus infinity, but it grows in a controlled way. It's a most exponential squared. Okay, and because of that, if you basically multiply by a Gaussian, it becomes a finite measure. And this is interesting for the point of view of entropy because of the following remark. Let me first observe a change, sort of a change of reference measure formula. Say that you have two measures, m tilde and absolutely continuous with respect to m. Say m tilde equal eta m. And let's say that you have a measure mu, let's say, that is also absolutely continuous with respect to m tilde. So in particular, is also absolutely continuous with respect to m. Let's say mu is equal to rho m. And let's say I want to compare the entropy of mu with respect to m and with respect to m tilde. Okay, let me just do algebra. So the entropy with respect to m tilde of mu, well, this is the integral of what? I should write, the density of mu with respect to m tilde, log of this density, dm tilde. Right? Then, of course, let me simplify and let's just compute the density of mu with respect to m tilde. And this is equal to what? This is equal, density of mu with respect to dm with respect to dm tilde. So this is equal to the integral of log of, so d mu with respect to dm is rho. Dm tilde, so this is this, right? Dm. Okay, so this is equal, let me continue. This is equal to the integral of log rho d mu minus the integral of log eta d mu. And of course, this is the entropy with respect to m of mu. So basically, the difference between these two entropies is the integral with respect to the measure mu, whose entropy we are calculating, of log of the density of the measure, one measure with respect to the other. Okay. Why is that interesting? Well, because now let me this is just a technical point, but I see people getting confused about this. So for once, I want to make this computation. And so what we just learned from here is that if I define m tilde, I mean if I define m tilde to be a normalizing constant e to the minus this c prime distance squared x bar m, then for c prime big enough and c normalizing, this is a probability measure. Right? Now I apply this formula over here, in some sense in reverse terms, and I deduce that if everything goes well, in some sense, if all the computations are justified, the entropy of mu with respect to the initial measure, which is possible, of infinite mass, is the same as the entropy of mu with respect to m tilde. Okay, and then there is plus the integral of the log of this with respect to mu. And what is the log of this? Well, the log of this is, well, first of all, I have a log of c, which is constant, and then I have minus c prime, the integral of distance squared on x bar d. Okay. So what it is that we can, so anytime we have a space whose reference measure m is possibly plus infinity, but after normalizing with a Gaussian kind of factor becomes a finite mass, I can define the entropy like this for every mu in P2x. You remember, I guess it was either the first or the second lecture, I mentioned that when the reference measure is plus infinity, you need to be careful about defining the entropy because you could have this, minus infinity going on. So it could be in principle not well defined. And there is a so basically you don't want your measure mu to be too much distributed with respect to how much mass the reference measure is giving to big sets, basically. Now what I'm telling here is that if the mass of the reference measure does not grow more than this exponentially squared away, okay, then it is sufficient for the reference measure mu to be in P2, so a finite second moment, to have a well-defined entropy. You see now this is well defined. If mu is in P2, this guy is well defined because I'm tilde is probability. This is a number, and this is finite. Okay. So this, I can take this as definition of entropy in whenever this is a finite measure, and it is clearly W2 lower semi-continuous, not weakly lower semi-continuous. I don't know whether it's weakly lower semi-continuous because there is a minus in front of here, and I have the sort of the wrong lower semi-continuous on this side. But if I'm weakly converging plus my second moment do converge, this guy which has the wrong sign is converging, and this guy is lower semi-continuous. Okay. Is there anything else that I want to mention? Okay, just a couple of more things, and then for today I stop. First of all, maybe I don't know if if it is clear from the sketch of the proof that I gave, but the importance of insisting on having measures with finite entropy when asking for the existence of the geodesic interpolating this is to get this stability of the CDK infinity condition, because the finiteness of the entropy enters into play in getting the compactness of the approximating geodesics. If you don't have this, you don't have compactness, and I don't know how to actually, at some point you have to, so if you want to prove stability, you have to exhibit existence of limit geodesics such as something is true. And if you have to exhibit something, compactness typically, should be there, okay, as a heuristic. So that's one thing. And okay, let me perhaps just present where we will go in 2 weeks from now. So what we have proved today is well, this theorem. CK infinity, CDK infinity is stable, which is a consequence, as I mentioned, can be seen as a consequence of the stability of convexity or K convexity with respect to gamma convergence. Okay? Now, here is an interesting point about convex functions. Let's think about, on RD. If you have a sequence of convex functions that is converging gamma pointwise uniformly, whatever you want, to a limit convex function, to a limit function. Well, then, first of all, the limit function is convex. And second thing, the subdifferentials, if you know what it is, of this approximately convex function do converge at the limit subdifferential. Okay, so in some sense, once you have convexity and and the stability of convexity, for free you get the stability of a first order condition associated with this convexity. Okay, and that will be our screwdriver to enter and make actual analysis on these CDK infinity spaces. And the guiding principle is the following. I will write a sentence. So the heat flow is the W2 gradient flow of the relative entropy. Well, the gradient flow of the relative entropy with respect to the Warston geometry. W2 distance. This is, an important and very important statement by Jordan Kinderlehrer. They made this observation on RD. And of course, if you so maybe you don't know what the gradient flow is, but as of now you know what is the heat flow, and you should know by now that this is an important concept. You know what the entropy is, and this is an important concept. And this guy, you know what this is, and this is an important concept. So perhaps it's a good idea to understand what this is, because it provides a link between these three concepts. Okay, and even if Jordan JKO, as they're called usually, idea, were born in RD, they provide us an angle to maybe possibly, if we understand what it is, maybe we can define the heat flow as a gradient flow of the entropy with respect to us at least. Those two Villani gave us, this CDK infinity condition that tells you, if you combine entropy and W distance in such a way that things are convex, then you are in an interesting class of space. Jordan Kinderlehrer tells us, look, if you take the gradient flow of this function with respect to this distance, then you obtain an interesting flow, which is the heat flow. Well, then perhaps why not start studying the heat flow from this metric perspective as gradient flow of the relative entropy, and as we will see, the fact that A, this heat flow is well defined in this class of CDK infinity space, and B, it is stable, is the cornerstone of the stability theory for differential operators in this CDK infinity. Okay, so in 2 weeks from now, so the next lecture is in 2 weeks, because next week there is a conference, and the 10th of October is holiday, Monday. So on Friday in 2 weeks, we will start discussing what it is a gradient flow in a metric set, and we'll try to make rigorous this. Okay, that's it. Sure, please. Sobra to the other RCD for sure. I think also CD actually. We can maybe, they don't know what this is. Maybe we can discuss this in a second after the lecture. I think CDK infinity is sufficient, and I think I have an idea of the proof. Let's comment on this in a second. Okay. Okay. Goodbye to